Math 2414, area between curves. Area between curves, example 5. But what if the equations are functions of y? In the previous video, I said, what do you do if your equations aren't functions of x, ... What if the equations are functions of y? And you may notice that this is the exact same problem as before. If you didn't watch the previous video, you should probably go watch it now. And being the same graphs, and it's the same lamina with the same area, so we should get the same area we got before, which was 18. But the problem with this previously was that the second equation was not a function of x. And to just recap it so this video can stand on its own. This was a sideways parabola that lived over here. This was a line that crossed the parabola twice, not drawn to scale. And the problem we had was twofold. Number one, the parabola is not a function, but if we looked at the top half separate from the bottom half, it's two separate functions. Number two, the bottom of the lamina changed from the parabola to the line at this point, meaning that we had to set up two integrals. One for when the top was the parabola and then the bottom was also the parabola, and the other for when the top was the parabola but the bottom was the line. And we got through it eventually and the answer was 18. But knowing what these graphs look like, and I'm not going to replicate the graphs like I did before. That's what consumed a lot of time in the previous video. But without rehashing everything that happened, this was the graph of y squared equals 2x plus 6. It had a vertex back here at -3. Its intercepts were positive, negative square root of 6, but I'm not worried about that. And we also had this line, which was y equals x minus 1. And we did know that the intersection here was at -1, and the intersection here was at 5. So that's what we knew last time. The line is a function of x, but the parabola is not because it fails the vertical line test. But what you may or may not know is both of these are functions of y. Now what do I mean by that? That means for each y there's a unique x. So for example, if I go to this y, there's only one point on the parabola. If I go to this y, there's only one point on the parabola. If I go to this y, there's only one point on the parabola. And of course one point on the line in each case as well. But the way you can tell that a graph is a function of y is if it passes the horizontal line test. The vertical line test answers the question, are you a function of x? The horizontal line test can answer the question, are you a function of y? And what I mean by the horizontal line test is that on the parabola, a horizontal line would only cross it once. These are both functions of y. Now why does that matter? Because if we go back over here, the names x and y are totally arbitrary. Who decided to call this the x-axis and the y-axis, and why wasn't it the other way around, and why those letters? Variable names are so flexible that anytime you say something using one variable, you can almost always change it to the other. If f of y is greater than or equal to g of y, two functions of y on some interval, then the area between the graphs of x equals f of y and x equals g of y is f of y minus g of y dy integrated from a to b. Most folks will call this interval c to d. For some reason, they're scared to call it a to b because we use that on the x-axis, but whatever. So we can play the exact same game from the y perspective, which means we need to figure out a little bit different information. What are these as functions of y? Who's on top and who's on bottom? Is that even the right question? And what are our limits of integration? Well, let's start by answering how to write each equation as a function of y. To write an equation of a function of y, it has to be in the form x equals stuff with y's. So in other words, we solve for x. Listen closely. To get a function of x, you solve for y. To get a function of y, you solve for x. If I solve this line for x, I get x equals y plus 1. Move the 1 to the other side. So we will call this function, we'll call this one f of y is equal to y plus 1. Give me a y value, I'll do something to it and produce the x value. We can solve this one for x, and it won't be a problem because there's not a square on the x. But if we solve this for x, we can move the 6 to the other side and then multiply everything by a half. 1/2 y squared minus 3 is equal to x. So we'll call this function g of y is equal to 1/2 y squared minus 3, which clearly is the parabola. So here we have f of y is equal to, don't need that anymore, y plus 1. And here we have g of y is equal to 1/2 y squared minus 3. And these are the bounds for the lamina. Who's on top and who's on bottom? That's the wrong question to ask. Because this integral is going to be a dy integral, we're not integrating from left to right. We're integrating from top to bottom, so you have to tilt your head and change your perspective. Because now the question isn't who's on top and bottom. That's measuring f of x and g of x, the y coordinates. We're measuring f of y and g of y, which produce the x coordinates, so we're not talking bottom to top, we're talking left to right. On this lamina, the parabola is always on the left side of the lamina, it's the left boundary, and the line is always the right boundary. Think of it this way. If we were to cut this into rectangles a la Riemann sum, and set up a rectangle like this and moved it from left to right, the bottom of the rectangle would change right here at this point. But if we set up horizontal rectangles and moved them from bottom to top, who's always on the right side of that rectangle? The line. And who's always on the left side of that rectangle? The parabola. There is no switching of who's on the left and who's on the right, like there was a switch from who's on the bottom at this corner, which means we only need one integral. The area of this is going to be the integral from numbers we haven't figured out yet, so a to b, of the right minus the left. So it's not top minus bottom, it's right minus left. The only thing that remains, aside from doing the integral, is figuring out the intersection points. But we can figure out the intersection points the exact same way we did before by simply equating these and solving. So for the intersection, we would just have to equate these two functions. 1/2 y squared minus 3 is equal to y plus 1. This is a quadratic equation, it's got a fraction. Get rid of it by multiplying everything by 2. Y squared minus 6 equals 2y plus 2. I just multiplied both sides of the equation by 2. Get it equal to 0 by clearing out the right side. And in general, when you're solving a quadratic equation, it's usually best to keep the squared term positive, which is why I'm emptying out the left side, the right side. Subtract 2 from both sides, subtract 2y from both sides. That zeroes out the right side. We have only the y squared term, we have only the minus 2y term, but negative 6 minus 2 is negative 8. This factors into y minus 4 and y plus 2. And setting each factor equal to 0 and solving would give us y equals 4 and y equals negative 2. That tells us that the bottom of this lamina is at negative 2, and the top of this lamina is at 4. And we could actually confirm that with what we found out earlier. Remember that this was x equals 5. Well, if I put 5 here, I get 5 minus 1 is 4. And remember at this one, x was equal to negative 1. And when I put negative 1, because it's on the line, negative 1 minus 1 is negative 2. But that's assuming we did all that already. But we got the same points in terms of bottom and top. All right, so now we know the limits of integration. The bottom of this lamina starts at negative 2. The top starts at 4. And just a reminder, we're kind of doing a Riemann sum thing. Riemann sum is cutting rectangles and add them all up. This is like a rectangle, but we're cutting it horizontally. The skinny side is represented by the dy. And so we slide this rectangle from bottom to top and then do the Riemann sum, which is why it's going from negative 2 to 4. This integral is much easier than the previous one. Let's knock it out. Negative 2 to 4, y plus 1. Distribute the negative to get negative 1/2 y squared plus 3 dy. We need to combine the 1 and the 4, but for the sake of time, because I've been here for a while today, I'm going to integrate and combine at the same time. Ooh, that's dangerous. If I integrate negative 1/2 y squared, I get y cubed times 1/3, reciprocal of the 3, times negative 1/2, which is negative 1/6. If If I integrate the y, I get plus 1/2 y squared. And if I combine the 1 and the 4, the 1 and the 3, I get a plus 4, and the antiderivative of that is plus 4y. And we evaluate that from -2 to 4. All right, let's finish this. If I put in 4, I'll get -1/6. 4 cubed is 64, so I'm going to go ahead and call it -64/6, which I know reduces, but we'll leave it like that for now. Plus 1/2 times y squared. 4 squared is 16. Excuse me. Half of 16 is 8. Plus 4y, so plus 4 times 4 is plus 16. Minus, if I substitute the -2, watch your signs. -2 cubed is -8. Negative times negative is positive. 8 times 1/6 is 8/6. I may go back and reduce both of these fractions in a moment. -2 here is -2 squared is 4, times positive 1/2 is positive 2, and then positive 4 times -2 is -8. And yes, I am okay with you going from here to here in terms of showing work. I'm going to go ahead and reduce these fractions because they both reduce to thirds. 8/6 reduces to 4/3. -64/6 reduces to -32/3. And I'm going to get a common denominator in a minute, but let's go ahead and combine fractions. Actually, that'll eliminate the need for a common denominator. You'll see why. -32/3 minus 4/3 is -36/3. But that's just -12. Thank you for playing fractions. It's been fun. Plus 8 and plus 16 is plus 24. Let's put together the integers here. Positive 2 and -8 is -6, but it's minus -6, so it's plus 6. -12 and 24 is 12, plus 6 is 18. It's the same answer as before. Thank goodness, I was afraid I made a mistake last time. So the moral of this story is y equals f of x is everybody's comfort zone, but equations don't always play like that. If you ever see a y squared, an absolute value of y, or in general, a y with something done to it, there's a good chance that your equation is not a function of x, but a function of y. But the consistency is, if you can isolate the y easily, you're a function of x. If you can isolate the x easily, you're a function of y. So you do have to learn to shift your perspective in terms of x's and y's. Last comment. And this goes back to what we did in the previous video to graph that parabola. Remember when we graphed the parabola by switching these, graphing it that way, and then switching it back, basically flipping that parabola across a diagonal? The truth is, and I hope I don't regret saying this, if I totally switch the x's and the y's in both equations, this entire picture would get reflected across the diagonal, but it wouldn't change the shape of this lamina. Meaning, if everything is a function of y, you can literally change all the x's to y's and y's to x's and do the problem that way and get the same answer. Ooh, that was sneaky. All right, that's it for this one. That didn't take as long as I thought.